So, one last example to figure out from the 19 examples we started last time. How'd you guys do this one? Yeah?
It's basically just going over that and then the derivative of
So you want to apply ddx of ln of u is u prime over u. So 1 over, when you're thinking of this as the u, it's 1 over that times the derivative. There's an easier way. Anyone do it a different way? Yeah?
first line distributed.
What? How?
So I'm going to ask ln 2x plus 1 to the 8
Minus ln squared plus 1 to the fifth. Why are they doing that? Okay, and then right, so at this point you can find the derivatives relatively easy. Right, so we use a constant factor rule. You just have an 8 here times, how do you differentiate this? Right, now you apply this rule, and it's a lot easier to apply that rule. This equation. Minus 5 times 2x over x squared plus 1. So this just becomes 16 over 2x plus 1 minus 10x over x squared plus 1. That's your answer. Which is a lot easier than actually applying this directly, right? Because you have to do like the quotient rule with the chain rule, then divide by this whole thing. You have to do keep, change, flip. You have to then simplify a bunch of stuff. The answer you guys is going to be equivalent to this, but you'll go through a lot more pain getting there than you have to. So this goes to show one of the things that I mentioned last time. Try to simplify before taking derivatives. You want to apply the simplest rules you can get away with before you have to escalate it to more complicated rules. So apply your algebra rules before you have to apply the calculus rules whenever possible. So in other words, especially if log is involved, try to apply log rules before. In fact, one of the things we want to talk about in the section I'm about to cover is because logarithms can make a lot of complicated situations into simpler situations, there are going to be times where we're going to artificially put a logarithm into a problem that it wasn't there before, just so that we can take advantage of the log rules, right? So if your log starts out being there, you're actually in a pretty good situation. Apply the log rules before doing the calculus. It actually makes your life a lot easier. And so always be aware of that. Always think simpler before you think harder. The algebra is nicer than the calculus. Just get through the algebra first, then do calculus if you have to. You'll have a lot easier time of it. If you just directly jump into this rule, it'll be a lot messier than what happened here. And some of you probably did that, would realize how messy that's going to get. You're not even going to take the time to write it out before it's that messy. So that's how I would finish up the last problem. Take advantage of the log rules, then the calculus, applying the calculus rules are going to be scarily easy. Move on to the next section, 3.5. I want to talk about a concept called implicit differentiation. And basically what I just mentioned, we're going to also talk about logarithmic differentiation. And that's kind of where we use a logarithm to make things simpler so that we can find derivatives. Talk about two different kinds of differentiation. So first let's talk about where does the word implicit come from? What's the difference between implicit differentiation and regular differentiation? So here's the idea. There are two main ways to define a function. So remember, a function is just a rule that tells you, if I give you an input, here's how you compute a corresponding output, right? So that for every input you give me, there's only one corresponding output. There are two main ways to actually write down a function in terms of its formula. One is called the explicit way, or explicitly. Now, explicitly basically means your y is isolated on one side. It is explicitly out in the open. And on the other side, you have some formula with x's potentially that's going to tell you how to compute a new y value if I give you an x value. So we've seen guys like this all the time. Y equals x squared is an explicitly defined function. Y equals x plus 1 over x plus 2. Y equals the square root of 1 minus e to the x. Like all of these are explicitly defined functions. And how would I go about finding derivatives in this case? Like how would I find dy dx? Well, how we've been finding it throughout all these examples, how we've always found them, right? Apply some derivative rule that you would have had memorized to the right side. There's another way to define a function though, and it's called the implicit way to define a function. So you can define a function explicitly and implicitly. And what implicitly means is the formula for the function is implied. You don't really know ahead of time what it is. So it would look like some rule where the x's and y's are potentially mixed together. So for example, x times y equals 1 is an implicitly defined function. Y is implicitly defined. Or the equation of a circle is an implicitly defined function, right? X squared plus y squared equals 1, right? Your y isn't isolated, it's not out in the open. Or something a little more complicated, x cubed y squared plus 2xy minus ln of y equals 17. This is an implicitly defined function. You don't have your y isolated on one side with only x's on the other side. Your x's and y's are kind of mixed up together. And the thing is, oftentimes when you're trying to apply mathematics to some real world situation, you're trying to figure out something in the real world. In a perfect world, everything will come to you into this nice formula where what you want, what you care about is isolated and you just have to worry about these other things. In real life, that doesn't happen. A lot of times you stumble upon some relationship through probability or statistics or just taking measurements or sciencing out something. The relationship comes to you in this form, right? Your inputs and outputs are kind of mixed together in the relationship that you came up with. But the thing is, we still want to be able to do calculus in this situation. We still want to be able to find a derivative. How fast is this thing moving in relation to that thing? We still want to talk about, is this thing increasing? Is it decreasing? We're still going to want to be able to talk about everything calculus allows us to talk about in this situation. And what implicit differentiation is, it's differentiating in this situation, right? When I don't have my y nicely isolated on one side, how do I go about taking derivatives? And that's going to be the main discussion in this section. And it turns out the answer is actually quite simple. Can actually explain in a phrase what you have to actually do, but of course we're going to get some practice doing it. In the implicit case, find y prime, more specifically dy dx, where I'm thinking of x as the independent variable and y is just some function of x that I don't know about, via the main rule is the chain rule. So I mentioned how important the chain rule is, and the chain rule comes to the rescue in this situation. Let me show you some illustrative examples for how this thing would actually be applied. So I'm going to show you how would we find the derivative of some functions where there's an f of x present that I don't really know what it is. And I'm going to show you the trick to actually finding a derivative in this situation is to actually use the chain rule. We're going to see what it would look like. Let's do another one. Say derivative of f of x squared. Derivative, say ln f of x. Derivative, say f of x divided by x. So I'm going to do the hardest one. You guys are going to help me with the rest. And just by following my cues on the first one that I do, you guys will have an idea of how to do the other ones. Okay, so I'm going to do this one. Really hard. Okay. How do I find the derivative with respect to f of x? Well, that's f prime. Okay, now you guys go. How do you find this derivative? X times f of x, right? So f of x is some function. I'm not telling you what it is, but it's hidden in there. How do you find x times f of x? Yeah?
X times f prime x plus f of x.
How did you get that?
Using the product rule.
It's in the product rule. We learned about that last time. Notice that what we have here is two functions multiplying each other. So that means the product rule should take effect. So what I'm going to do is I'm going to, this is like my f and this is some other g. Right? So I know that this should give me f prime times g plus f times g prime, where my g is just the x. So I'm going to go derivative of f, well that's f prime, times g, which is x, plus the f, well that's f of x, times g prime, which is 1. Great. What does this one look like? Or maybe let's do this one first, it'll probably help out with that one. How do you do this one? So there's some function squared. How do you find the derivative of that? Yeah.
Would it be
2 f of x times prime. How did you get that? Well, it's almost a power rule, but there's an inside function. Why did you multiply by the derivative here?
So you exponent 2 times that.
This is, you're differentiating the outer function, which is the squared function. You multiply by the derivative of the inner function. Essentially what you applied here was the chain rule. And another way you can think about what's happening here is also the chain rule. What does it actually mean to find the derivative of f? One way you can think about this is that I'm finding the derivative of some inside function, right, to the first power. And then I can bring the first power down, subtract 1 from the power, multiply by the derivative of the inside. But of course, f to the 0, that's just 1, so you really get that just simplifies to f prime. Right? So you're applying the chain rule here, you apply the chain rule here, because when you don't know what the function is, it's some inside function, the chain rule is the rule that allows us to find the derivative of that. That being said, how do I differentiate this now? Product rule, again, two functions multiplying each other. So you differentiate the first, leave the second alone, plus leave the first, differentiate the second. So derivative of the first, 2x, I'm going to leave the second part alone. Plus, I leave the first part alone, what's the derivative of the second part? 2f of x times f prime, right? So notice that whenever I'm differentiating something that's not just an x, or I have to multiply by the derivative of that thing because of the chain. How would I differentiate this one? Yeah. U prime over u, which is going to be f prime over f of x. Remember, we derived the u prime over u formula using the chain rule. You do this one, f of x divided by x, derivative. Quotient rule, right? It's a division of functions. So, what would that look like? F prime times x minus things I want you to get from this. First of all the old derivative rules and formulas that I told you about, they still apply. The product rule still applies, the chain rule still applies, the quotient rule still applies, all that stuff still applies. How you differentiate ln of something still applies, that all applies. The difference is, whenever there's a function in the way that you don't really know what it is, that f of x could be anything, how you deal with that is the chain rule. You think of it as an inside function. Whenever I'm differentiating the f, if I have to do something around it, I just need to make sure that I'm multiplying by the derivative after I do that. So there's an f prime, and that's visible. There's an f prime. So every time I'm differentiating something that's not just an x, I have to multiply by a derivative. Why? Because of the chain rule. Now, oftentimes, this isn't going to be how it's presented, but I wanted you to get an idea of seeing it this way before I show you how we're usually going to have it presented. So, pretty much going to do the same examples, except now I'm going to have like a change in notation. So, instead of f of x, what if I just wrote y? Back to the beginning. What does this look like? d dx of y. It's just y prime. What if I have x times y and I find the derivative of that? What would that look like? X prime, which is 1 times y. No. Prime, right? The y is just taking the place of f. So you have to write out the prime. It's not okay to just kind of ignore it. Because it's not an x. It could be something that's there, right? It could be like an e to the x here, which you know you have to multiply back by the e to the x. What's this one going to look like?
2x
Mm-hmm.
times y squared plus 2y times y prime times 2x.
Times x squared.
X squared.
So here you differentiated one function of the other. So this is like your f, that is like your g. So what you did was f prime times g plus, here's your f times g prime. Now when you're finding the g prime, what you have to recognize is that your y, there's an inside function here. So it's not just a y squared, technically. It's some whole function squared. So there's an inner function. So what you do is you differentiate around it, 2y, but then because you know it's an inside function, you have to multiply by the derivative of the inside function by the chain rule. So that's what that derivative is. Y squared, 2y prime. Again, y is an inside function. So I have the square of it, the square is the outer function, differentiate around it, and multiply by the derivative of the inside.
Y prime. Y prime times x minus y times y.
So you're applying the same rules. The difference is every time you see a y, you have to multiply by a y prime, is essentially what you want to take away from it, right? We're going to generalize that a little bit moving on, but for now, just think of it that way. Right? Everywhere you see a y, you want to find dx. You have to multiply the y term by a y prime. When you're differentiating an x part, it's just like usual, how you normally differentiate an x part. Whenever you're differentiating a y part, a multiplication by y prime has to occur. And that's basically the main idea behind implicit differentiation. If there's a function mixed up that I don't know what it is, I can just differentiate it like it's an inside function and multiply by the derivative at the end of the day. Now, how does that actually help us with derivatives in some of the situations that I mentioned before? So let's actually put this into practice with some examples. So the example is to find y prime, which is dy dx. So the first example is, suppose we know that x times y equals 1. How would you go about finding y prime? And so if you want to use implicit differentiation, so notice that my y is not isolated. But I still want to be able to figure out what is the derivative of the y function. Here's what you would do. You would differentiate both sides of the equation. And now what would that look like? So if I want to differentiate the left side, right? I want to differentiate x times y. So now we probably know how to do that. What would the derivative of x times y look like? Yeah.
Y plus xy prime.
Right, because you're doing the product rule. So it's the derivative of x, which is 1, times the y, plus you leave the x, differentiate the y. What is the derivative of y? Well, it's y prime. There's some inside function, I don't know what it is. Whatever its derivative is, y prime is what it is. Derivative of 1?
0.
0. Now, by differentiating both sides, what you will now notice is that you are going to have an equation where y prime is one of the members, or I guess several members, of that equation. If you want to find y prime, what you need to do is just solve for that thing. At this point, it's just algebra. You already did the calculus. How do we solve for y prime?
Just isolate it.
Isolate it, exactly. How do we isolate it?
So it's it'll be like negative y over
Subtract
x
y, then
over x.
divide both sides by x, and that's your answer. That's y prime. One issue. How do you know that you didn't divide by 0 here? Can x be 0? And division by 0 is very bad. sure. Yeah?
It can't be 0 because the equation originally is equal to 1.
Right. So we know x is not 0 because if x was 0, that would be 0. So divide by x, that's a valid move. That's my answer. So that's what y prime is, minus y over x. Now, might be a little squeamish here because your y, notice that you have a y in the answer, which is probably strange, but it's not going to be strange after a while. So here's something else I wanted to consider here. Suppose I did not want to use implicit differentiation. Could you get that done without implicit differentiation? What would you do? So, yeah.
You just divide by x.
You can divide by x. Again, you're not dividing by 0 because, you know, if your x was 0, that wouldn't be 1. And how would you find y prime now? Take the derivative. What is the derivative?
Negative 1 over x squared.
Minus 1 over x squared, right? That's the formula that we had memorized. Right? You could also think of this as x to the minus 1 and then do the power rule. But I think 1 over x, we already had that memorized. Okay. So, now comes another question. So, according to what we've been doing it the old way, that's the answer. Using implicit differentiation, that's the answer. Are these answers equivalent? I mean, is implicit differentiation a hoax? Like, is that wrong? Is that, like... I mean, it should make sense. We're applying the chain rule and we believe that the chain rule is correct. How do you explain the discrepancy between these two answers? Or is there actually a discrepancy? Yeah? Yeah?
Well, for implicit differentiation, we took the derivative of 1, but we don't. I don't know.
They're the same? How do you know that?
If you plug in negative 1 over x squared so if you do negative 1 over x squared, there's negative 1 over x, multiply that over, isn't it just?
Oh, you're assuming they're equal in the first place.
Yeah, just
So-
test that.
Without really assuming these two answers are equal, how can you know that they're the same? So according to one of them, y prime is minus y over x. How do you know that this expression is pretty much the same as this expression? Ideas? So what's the main difference between these two? I mean, yeah, they kind of look different, but the main one is, whenever you don't use implicit differentiation, y is not a part of your answer. Y is a part of this answer. So maybe you might want to think of getting rid of that y. How do you get rid of that y? Yeah?
You could like make the original equation that you started out with to be explicit,
Okay,
and
so,
then you would plug that in for y.
right, so what is your y?
Y would become 1 over x.
Right, your y is actually a 1 over x. Right? So when you say minus y over x, what you actually have is minus 1 over x over x. And what is that? It's actually minus 1 over x squared. Right? So the answers are actually exactly the same. The difference is, in this one, y is defined implicitly. You don't really know what it is in the beginning, but it turns out if you could figure out what it is, it's actually equivalent to you having the answer in the explicit way the whole time, right? So I just wanted to convince you that when you do implicit differentiation, your answer might look like it's in a weird form. You might see y's all over the place, but you don't have to worry about it, because if you could solve for the y, it will be equivalent to the answer you would get had you done that in the first place. So that's the first thing I want to talk about. The next thing I want to mention is this example might make it seem like, why implicit differentiation? Like, why didn't we just do this and just do what we always did? Like, why is there this whole new complicated way? Are you just messing with us, Jhevon? Like, why do we need to know this? Okay, let's move on to the next example. So, same thing, I want to find y prime. And here's the thing I want to find y prime in. So you have that relationship. You want to find what is the derivative of the y function. Question, could we solve for y here? Can you solve that for y? Yeah? You see, how would you solve for y?
Divide, move the 5x squared plus 2x over
Okay.
to the side, divide x to the fourth.
Well, no, because you're going to have a y here. So you get a y over x to the fourth plus y squared equals the 4x cubed over blah, blah, blah. So you wouldn't be able to solve for y that way.
Can't you just divide the 5x squared plus 2x to the other side so that y stays on the left side? And then you get y plus x to the fourth y squared.
No, because in an equation, you'd have to divide both sides by it. So if you want to divide by the 5x squared plus 2x, what it would look like is y plus x to the fourth y squared over the 5x squared plus 2x equals the 4x cubed over the 5x squared plus 2x. That's what it would look like if you just divide both sides. Right? And so you can't isolate y. I'll give you a hint. You can solve for y, and here's a hint as to probably how you can see how you'd be able to solve for it. That equation is exactly the same as this equation. Now do you see how to solve for y? Quadratic formula. It's quadratic, right? It's just a weird way of writing a quadratic, right? This just looks like ay squared plus by plus c, where that's my a, that's my b, that's my c. Right? So it's actually a quadratic equation, which means I can solve for y using the quadratic formula. Y is going to be equal to minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So now, the question is, would you want to find y prime for something like that? Doesn't look like a lot of fun, and I can assure you, it's not a lot of fun. Right? You can go home and do that on your own if you want to convince yourself how not fun that would be. We're not going to do it. But yeah, find a y prime. So you might think of this example, well, why do we need this guy? I mean, we could have just solved for y and just do it the normal way. Here's what you would get if you're dogmatic about that approach. You know what, I'm always going to solve for y, just do it the old way. I don't want to learn this new thing. Right? You end up in situations like this. Okay, so suppose we don't want to do that, because I don't think we want to do that. Right? That's going to take like the quotient rule with the chain rule, and you'll get a lots of mess. So let's do this implicitly. So let's not isolate the y, but still go about finding derivatives. How would we actually accomplish that? Okay. Now, applying implicit differentiation, how would we do that? Well, you're just going to differentiate both sides of the equation. So you're going to differentiate this, differentiate that, differentiate that. Then you're going to isolate the y primes. So, how do you differentiate this? So we're going to differentiate one term at a time. So the first one is this guy. How do you differentiate that? Yeah? Product rule? Right, so what is that going to look like?
So you got 5x squared plus 2x times y prime plus 10x plus 2 times y.
Right. So you differentiate one, leave the other, plus differentiate this one, leave that one. You apply the product rule. When you're differentiating the y part, multiply by y prime. Plus, or you differentiate this guy, the x to the fourth. So another product rule. What is it going to look like here?
4x cubed times y squared plus x to the fourth times 2y
Times y prime. Differentiating the y part, you multiply by y prime because it's an inside function. We don't know what it is. It's just some inside function. That's the derivative of the second part. How do you differentiate the 4x cubed? 12x squared. So you went through and you did calculus just now. You found all the derivatives. But of course you want to find y prime. So your y prime is here, and you have a y prime here, and you want to essentially isolate it. How do you get that to work out? How would you solve that? Yeah?
Put the other things on the opposite side of the equation so that you just have the y.
Subtract this, so I'm gonna have the 12x squared minus the 10x plus 2. Subtract that, so I'm gonna have the minus 4x cubed y squared. And on this side, I'm going to have two guys left with the y prime, so this that's this guy. And I'm going to have like the 2x to the fourth y prime, which is that. Now what? Yeah?
Take out y prime.
Y prime is a common term.
Divide the rest.
And now you just divide by that whole thing. So you get y prime is going to be equal to x squared minus 10x plus 2y minus 4x cubed y squared over 5x squared plus 2x plus 2x to the fourth. And that's your answer. That's y prime. Now, that looks a little messy until you consider the fact that had you gone this route, what the answer would have looked like is imagine this whole thing plugged in here, here, and here, and imagine how monstrous that thing would look. That's what you would have to have gotten had you done this directly. Right? It's not going to be fun. But yeah, that's what the answer would look like with implicit differentiation. And It's easier than actually doing that one directly. So the calculus all happened in the second line. The rest of it is just a matter of algebra, just isolating guys and moving one to the other side. And yes, you have an answer, there are y's in the answer, but hopefully the first example convinced you that that's nothing to worry about really, because I just kind of know if I could figure out the y and plug it in there, it would be an answer that I would expect. It's not gonna be wrong, but that's a valid answer, it's a bona fide answer. So at this point, clearly the first example shows that we don't need implicit differentiation all the time. The second example showed, well, yeah, we don't need it, but it would be nice to use it because I wouldn't want to not use it. But here's another example. So kind of showing you in stages how important implicit differentiation is. It's not really something that we're making up just to give you busy work to do. It's something that's actually quite important. So again, find y prime is going to be the goal. And here's your equation. Now it's not going to look as crazy as the previous one. But that's the curve. And that's no random example. It's actually studied by a very famous person by the name of Descartes. It's called the Folium of Descartes. So Descartes, the guy who came up, I think therefore I am that guy. That's the guy. So he was also a mathematician, believe it or not just a philosopher, and did many great things. One of the greatest things he did was this was the guy who invented the XY plane. You know, the XY plane, like the idea that, oh, X is horizontal, Y is vertical. Like no one thought of that before that guy. You know, so he literally was like, you know what, I'm gonna use a picture to think about this equation. Like no one thought of that before him. Like pictures to represent an equation, what do you mean? So, you know, y equals x squared, well that's a formula. No, he saw it as a picture, right? This is that, right? And he had to invent the XY plane in order to do that. Right? But that guy, Descartes, came up with the idea for the XY plane. That's why it's called the Cartesian plane, right? The cart is from Descartes, right? So it has his name, the Cartesian plane, because Descartes came up with it. But anyway, this was something that he was studying. It's a curve that he was studying. It has this, the graph looks like this. So it's not a function. It doesn't pass the vertical line test. But it was an important thing for him to study at the time. Now suppose we are looking at the Folium of Descartes and we want to talk about rates of change. I want to talk about y prime. And you not being convinced that implicit differentiation is something that you would have to know, you want to actually go about solving that for y directly and then finding the derivative the old way. Because why am I going to learn a new way? If the old way, if it ain't broke, don't fix it. Well, it turns out that another mathematician is actually going to rain on your parade in this point, because it turns out for this particular equation, it's actually impossible to solve for y. And I don't mean it's hard. I mean literally impossible. Like there's no way to actually get it done. Like you can't do it, right? So we know that if you have like a quadratic, there's a quadratic formula. It turns out if you have a cubic, there's a cubic formula. If you have a quartic, there's a quartic formula. There are formulas for polynomials going up to the 4th power. A mathematician by the name of Galois actually proved that once you hit the 5th power and anything higher, no formula exists. You can't even write it down. Like there is no formula. There is no standard way to solve any polynomial that's of a 5th degree or higher. You might get lucky with certain ones, but in general, there's no general solution. And for this one, this is one of those ones where it has no general, there's no nice way to actually isolate the y. You cannot do it. You will spend forever trying to do it, and you will fail. You can't actually solve for y here, even if you wanted to. But suppose we still want to be able to do calculus. I still want to be able to draw tangent lines and talk about y prime and how fast is this thing moving. Implicit differentiation is now the only game in town. You don't have an option. You need it. You can't get away with not using it if you care about finding derivatives here, right? So, algebraically speaking, this equation is super hard to deal with because we can't isolate the y even if we wanted to. It's mathematically impossible. So, can we still do calculus? The answer is yes. How? Implicit differentiation is how. How do we go about finding y prime? This is where you guys come in. Yeah.
Differentiate like each part,
Mhm.
so 2x
Mhm.
plus 7, y is 6, y prime.
Right?
is
Multiply by y prime because of the chain rule. Every time you differentiate a y thing, multiply by y prime. Okay.
minus 2y prime equals 0.
We'll see. Now your y prime is just some guy in an algebraic equation that you want to solve for. So you're just going to isolate them. What you're going to do is you're going to have 7y to the 6y prime minus 2y prime. You're going to move this 2x to the other side. You're going to factor out the y prime. And then we're going to divide both sides by that thing. So it's 7y to the 6 minus 2. And that is going to be your answer. So that's how I can find the derivative, right? I can't even find the original function, but I can find the derivative. And that's because of the power of implicit differentiation. Now, there's a very valid concern that one might have at this point if you've been seriously thinking about the things I was saying. I said there's no way for us to figure out what y is. Like, we don't know how to find y. But the answer that I gave you for the derivative has y in the answer, right? So there's this thing that's impossible to find that my answer has contained in it. So yeah, we can do this answer, but is it just a party trick or is this actually useful in some way? And it turns out it's actually still pretty useful to have an answer in terms of a function that you could never find. And we'll talk about that next time. So it's coming up. So implicit differentiation, it allows you to find the y prime or derivatives. When your x's and y's are mixed up, your y isn't isolated. And there are some times where it's nice to do it, but there are other times where it's literally impossible to do it otherwise. So it's a very important kind of differentiation to know about, and we'll do many more examples. Also remember, we don't have class on Tuesday, right? Like Tuesday, I believe, is on Monday. So our next class is Wednesday, and that's when we'll have the quiz. And it's up to here, up to everything on basic differentiation. Know your derivative formulas, chain rule, product rule, quotient rule, how to differentiate exponentials and logarithms, and just how to find derivatives of specific functions. I'll see you guys on Wednesday.